In this video, we are looking at the polymer lab. And in the first part, we're going to look at the 10 questions and kind of see the different lab parts. And the second part, we'll do the recycle code activity. So I'm just going to go to a screen share here. And that is the intent. And we're going to grab the polymer lab, which you can find in Schoology. And hopefully you're seeing that right up there. So polyvinyl alcohol slime, okay? These polyvinyl alcohol slime is a polymer. I'm going to go to the very last page of this document where we actually made the lab. So if you were here in lab, you did this. If you weren't here, you probably made slime at some point. But we made 3 different types with slight variations in the ingredients. One was a polyvinyl alcohol slime, the first one, and that's kind of a clear substance. The second one is no food coloring in that one. Is a polyvinyl alcohol slime, which is similar substance, but it had Elmer's glue version. So slightly thicker thing, had a little food coloring in to give it its color. And then the third one was a guar gum slime. Okay, and that was just a little variation on polyvinyl alcohol, but quite similar. So we got 3 different slimes, similar properties and a lot of commonalities, but some differences there. All right, I'm going to go back to some questions that you have for this. So you can read through the introduction and some of those different things, but I'm going to give you some hints at the questions and then kind of link it back to some of the text. For these first couple questions, what is a non-Newtonian fluid? Give an example. Slime is a dilatant. What does this mean? So you can pick this out of what you read in the packet, or you could just go to a search engine or Google and just come up with a definition and an example for it. Definitely these slimes would be examples of a non-Newtonian fluid. Okay, next thing I'm going to do is just maybe talk about that a little bit, where it talks about slime being a non-Newtonian fluid and that is a dilatant. Okay, so it says it is a dilatant. And what does that mean? Okay, under low stretch, such as pulling material, flow and stretch. So if I look at this, this thing is, even though, is it a liquid or a solid? Well, it seems to be, thicker than a liquid, but not as thick as a solid. So it flows, but it flows slowly. And this is kind of just flattened out, laying on the table, and it will continue to do so with all these different things. So under low stress, it just kind of keeps flowing and stretching. If I put it under high stress, it snaps and breaks. So I could just grab one of these things right here. I think I'll grab the guar gum slime, and I have this piece here, a little bit like my flubber, and I can just kind of flows and oozes. But if I go quick, it'll snap or it'll break in half, come together. So those are a couple of the things that we see with slime, or slime that you probably worked with at some point. Okay, I'm going to go on and talk about the structure of these things. That's what's kind of asked about in question 3, but I'm going to give you a visual of this. So if you're looking at question 3, this is what we'll call a monomer of polyvinyl alcohol. So let's say yellow is hydrogen, black is carbon, and red is oxygen. So what I have here is a carbon, and it is bonded to hydrogen here, to an oxygen here. And then there's 2 sticks or 2 springs, which is a double bond to this other carbon right here. Okay, so it has 1, 2, 3, 4 bonds in this carbon, 4 bonds in this carbon. This is a monomer, okay? And this is another monomer of the same thing, so it's identical. What am I going to do with these 2 monomers? I'm going to break the double bond and link those together. So the 2 monomers become a polymer of 2 monomers. Now what happens when we're making some of these polymers, not only do we make like a polymer with 2 monomers, but it might be 20. In fact, it might be 200. In fact, it might be 2,000. So a lot of these slimes and goops are actually like thousands of monomers combined in one long strand right here. So that really is the polyvinyl alcohol right there. Okay, so if I look at this structure right here, I can see that I have a carbon and another carbon with an OH on it. This really is the monomer right here. Probably draw on there a little bit. Remember how to do this. Okay, so I could do a little circle. And really, this is the monomer part right here. Okay, and instead of the double bond breaks, and now it can connect to another one. And then we have another monomer here. And another monomer here. And it just goes on and on and on and on. Okay, sounds like a Journey song. So anyway, this goes on and on and on and on. And this could go on for a very, very long time with this type of structure. All right, so this is the structure for the monomer. Actually, that's a double bond, but it breaks to form that and it continues going. What about the what about the other one, the guar gum, is going to be very, very similar, except, and we will go to that page and go back to my spotlight and look at the next page, and you might see something like this. Now, let me erase this out. Done this in a while. There we go. And I look at this, and what does an R mean? That's just kind of the on and on with the carbons continuing. So it's very similar in structure, except it has 2 OH groups instead of 1. So this was the polyvinyl alcohol with 1 oxygen OH group on it. And this is the guar gum slime with 2 OH groups. Notice quite similar, and the products ultimately have quite similar properties at the end. So I think that'll help with like question 3 when you're working at it. What is cross-linking? I might show an example of that. That's really where we take these long strands. So this is a polyvinyl alcohol, a really long strand and a really long strand. That's going to flow. In the lab, we had the polyvinyl alcohol. Before we added the borax, which is a linker, which is the stuff that links things together, it just flowed. You know, it's maybe a little thicker than water, but it pretty much flowed like water. Then what we did, we put in the borax, and this kind of stuck these big long strands together and made it flow really, really slowly. So this will flow, but it's a lot thicker and it flows more slowly. Okay, I'm going to go on to question number 5. What ions are responsible for the polyvinyl alcohol monomers and the guar gum monomer for cross-linking? I think I just mentioned that. So just shortly, and then ago I did, and then consider the texture of products. Are these links relatively strong or weak? Well, compared to water, okay, they're looking, you know, they're stronger, but water doesn't really have any links. Compared to another solid, it would be weaker. So you kind of have something in between. Number 7, I think you should be able to figure out on your own. Think about the charge on boron. Look on the common ion table, think about what the charge on boron is. Look up in the common ion table what the charge of OH is, and then add those together. And you should be able to get a -1, so you can verify that or show support for that. Okay, here you'll have to understand what viscosity is, the definition. So I would look that up, and certainly Google that, and then see how that links back to what we're doing in the lab. And then the hint for number 9 and 10 is you have a polymer with a molar mass of 140,000 grams per mole. Okay, what I would do is take that and take the molar mass of an individual monomer, and then what are you going to do is take the 140,000 divided by the molar mass of the individual monomer, and it's going to give you an answer to that. It's probably going to be over 1,000 units long. So again, we get really, really, really long chains of these monomers in these particular polymers. And the same type of thinking goes with number 10, except for that is with the guar gum. Notice the extra oxygen here relative to this one right here. Okay, hopefully that helps with answering questions 1 through 10. And there will be another part that goes through the recycle codes part of this lab. Thank you for watching.